right, so we're going to start talking about vectors and where they lie in the R2 plane, the R3 plane, and then also kind of some extensions into what Rn might be. So we're going to start with R2. We call these vectors right here column vectors, and you can think of them as being like an x1, x2, or in R2, we can think of these as ordered pairs. So we can think of this as like x, y. Now, if you have two vectors, then the sum is literally just component to component. So you add across row 1, add across row 2, and you get your solution vector. And we'll look at what that looks like in the coordinate grid here in just a minute. Okay, all vectors have a magnitude as well. So if you have a scalar multiple, like here's our vector 3, -1, if you have a real number scalar multiple, then you are going to multiply that into both of your pieces of your both components inside your vector. So we get an answer like this. So let's look at our first example. Okay, so here's u and here's v. Let's find for u. So for u, now in the textbook it has it bolded. On our paper we can write it like that with a little vector sign on top. That's 4 times the vector 1, -2, and then I just multiply that component wise. So I get 4 and -8. All right, if I wanted to find -3 times v, then I'm going to take -3 and multiply that by the components in vector v. So that's going to give me 6 and -15. All right, my last one that I want to look at in this example is adding 4u plus -3v. Well, I know that 4u is 4, -8, and I know -3v is 6, -15, and so I'm going to add these component-wise. 4 plus 6, -18 plus -15, -23. Okay, and so that's how we're going to do some of our vector algebra, if you will. All right, so here's an example of how we write these vectors in the coordinate plane. So we again can kind of think of this as an x, y situation where A is your x and B is your y, that geometric point. And then in R2, we then take the vector to go from the origin to that point, okay, so that it has both magnitude and direction. Now, it is important to know that all parallel vectors, let's call this vector u, all parallel vectors to this that have the exact same magnitude and direction are just translations of vector u. So those would be equal vectors is what we say. It just doesn't start at the origin. But the original notation of this means start at your origin and then go to that xy in the xy plane or x1, x2 plane. All right, we need to talk about then what the addition rule does geometrically. So if I were to add together these two vectors, they have both positive components. I'm looking here at this picture. They have both positive components for x1 and x2. So it makes sense if I were to add those row-wise across that I would end up getting something else that is positive. One thing that I also want to show you is we said that u vector above, right, can be moved around and it's still the same vector. So you can add this by taking, like here is u, and then cutting and adding vector v. And notice I end up in that same diagonal piece here. That's the parallelogram rule for addition. Okay, u plus v is that vertex over here. You could add it the same way, and we'll see in the properties, v plus u. So v vector plus u vector, it gets you to that same spot. So it makes sense that that must be u plus v. Example 3, I just snipped it directly from the textbook so that you can see an example of when maybe one vector is in a positive positive and then one's in the negative positive. So again, I would just add these by going straight across. That's how negative 4, 3 happens. You can see I'm at the point negative 4, 3. That is the solution vector for the sum of u and v. Or I can think of, here's u, I could take v and then go in this direction, and it gets me to that solution vector there. All right, let's kind of look at these on our own and these geometric descriptions. So if u is 3, negative 1, then there's u. So then 2u would be 6, negative 2. Notice that's literally 2 lengths of u to get that to that point. Okay. Let's look at negative 2/3 u. Well, when I multiply negative 2/3 times 3, I get negative 2. Negative 2/3 times negative 1 gives me 2/3. And so now I'm going to be at negative 2 2/3. So I shorten this, and then notice the negative makes the vector go in the opposite direction because it reverses. If I had a positive x, I now need a negative x. I had a negative y, so I now need a positive y because of that scalar in the front. So I shortened it by a factor of 2/3, and I need it to go in the opposite direction when that vector has a negative scalar in the front. All right, here's all the algebraic properties listed out for you. I'm not going to go over them all. They're pretty self-explanatory. They're just normal algebraic properties that we've always used. So things like commutative, association, a zero property. So you can kind of take note of these and know that like the things we normally do in algebra, we can do with vectors. Two other quick content things here. If we are in R3, then I want you to think of this as being an X, Y, Z plane. So the vector 2, 3, 4 means X equals 2, Y equals 3, Z equals 4, or you can think of this as the X1, X2, X3 plane. And so you can see here now in that 3D that there's my A vector here. Twice of A would be that exact same direction, just twice the magnitude. If I have vectors in Rn, okay, we can't visualize that, we can't graph that geometrically, but we can think about this as being in the nth dimension. So that column vector is going to be an n by 1 column matrixy or column vector, and that's going to be in the nth dimension, or we call that in Rn. Also, it is possible, this kind of sneaks in here at the end, to have the zero vector. It just means that 0 is in every entry, okay? And it would have 0 magnitude because it would just be hanging out at the origin.